and I will explain some work about Selbert-Delange method. So I begin by some historical points. So let P is a set of prime and omega of n, the cardinality of the prime divisors of n. So pk of x will be the cardinality of the set of integer less than x, such that omega of n is fixed and equal to k. Okay, so of course, if I do historical presentation, I begin by Hadamard and de la Vallée-Poussin result about the prime number theorem. So, with our notation is P1 of x is equivalent to x over log x when x tends to infinity. Then Landau generalize this result with a pk of x. So for each k fx, we have the equivalent pk of x is equivalent to x times log x power k minus 1 over the factorial of k minus 1 times log x. So here, log index 2 is the log function. Okay. So now we have the result of Hardy and Ramanujan who prove an uniform upper bound. So pk of x is bounded by a constant times what the expected term, well, when k is not too big, but so we have this nice upper bound. So now we arrive to Erdős result. We prove an asymptotic uniform bond equivalent. So pk of x is equivalent to x log x power k minus 1 over the factorial of k minus 1 times log x, but uniform around log x. So I mean when the absolute value of k minus log x is less than a constant times square root log x. So now we arrive to closer result of our talk. So in 1953 and 54, Sate prove an uniform equivalent. So, but for for k minus 1 over log x less than 2 minus epsilon. So the equivalent is a function can be settled with a function lambda. So lambda is 1 over a capital gamma of r plus 1 and an Eulerian product. So the Eulerian product is a product over p of y minus p power r times 1 plus r over p minus 1. And so the equivalent is the product of lambda of r times the expected value, well, the equivalent in the Erdős results. And the way to prove it is really technical. He used an inductive method based on a functional equation of a pk star of x. So pk star counts only square free integer, and then you can deduce it using the factorization of n as a square free integer times a square. But it's a long proof, and then Selberg find a new method using analysis, a complex analysis. So he remarked that pk of x is a coefficient of the sum of n less than x of z power omega of n. So the kth coefficient. So using a complex analysis, you can use Cauchy formula, and you have this very nice formula. And why this formula is useful? Because now you need to estimate the sum of a multiplicative function z power of omega of n. And when you look at the Dirichlet series of this function, you find an Eulerian product, and you can approximate it by zeta of s power z times a convergent Eulerian product. So it's okay for S with a real part larger than 1, and of course you need to be careful for the definition of zeta of s power z when the real part of s is less than 1. But you have this Perron formula, and you know that around around s equal 1, zeta of s is can be approximated by s minus 1 power minus z. So using the Hankel formula, so I write it what I mean by Hankel formula. So capital H is a negatively oriented Hankel contour around S. So please find the drawing. And so it's very crucial for the Segber method to understand how we can handle this Hankel contour. So then we truncating the contour on using the holomorphic continuation of zeta of S in the 0-3 region. We get this estimate. So pk of x is approximated by lambda of r times x times log x power k minus 1 over the factorial k minus 1 and times log x. And the other term is k over log x, but it's uniform for k minus 1 over log x is less than b, but b is a constant, a fixed constant. So it can be here larger than 2. And to get this constant, you use the saddle point method to estimate the Cauchy integral. So this is a very efficient method, and it's a way to explain why you find this factor lambda of R. Of course, because you find it studying the Dirichlet series of z power omega of n. So please note that if R equals 0 on 1, you have a lambda of R is 1. Then after, Delange studies systematically summatory formula for coefficient of Dirichlet series which are close to zeta of s power rho. So this gives a new proof of Erdős-Kac theorem. So I mean the normal distribution of omega of n minus log x, which is the mean of omega of n, over the square root of log x. So it's a very nice result and very fundamental for probabilistic number theory. So using Selberg and Delange method, we can estimate the second term in the Erdős-Kac theorem. And we also be able to estimate the moment of omega of n minus log x in some sets, for example, for the set defined by the condition omega of n is congruent to A mod Q. So there is a much more example of application, so distribution of some subsequences on asymptotic expansion and so on. And so there is a very nice book of Gerald Tenenbaum where there is a very two nice chapter on Selberg-Delange method. So he gave effective form of previous result on a very nice surveys of this result. Some also new result. So if you assume that you have a function, not multiplicative, but just an arithmetical function which has a Dirichlet series close to zeta of s power rho. So I write it zeta of s power rho times capital G of s, and we assume on small g of n that we have such a bond. So you see that such a hypothesis do not imply that there is that J capital G of S as an holomorphic continuation. But if you assume that K is an integer, you have such a bond, you can prove an asymptotic for the sum of f of n. So we have a nice development plus an error term, like in Selberg-Delange method, and R of xf satisfy a general upper bound. So we have h of k, which is bounded as in our assumption. We have the error term of the prime number theorem, well, exponential of minus a times the square root of log x, and time. Oh, so there is some question. Oh, sorry. Yes, maybe there is a factor x. Sorry, in the upper bound. And the second term of the upper bound is x times a constant times k plus 1 power k plus 1 over log x power k plus 1. So if k is large, it's a accurate estimate. Okay, so there is also other hypothesis. You can assume that G of S satisfy an analytic continuation in the zero-free region of zeta of S. And if you have, so rho satisfies that the real part of rho is less than y minus epsilon, you can write the main term as a nice formula. So you have the sum of f of n is the integral between 0 and 1 of x power 1 minus t times this continuous function alpha of rho, index rho of t times t minus rho dt, and with a very small error term. So it's a nice result, and it can be useful in some application. Okay, so now I will speak about the same result with new hypothesis, so a weaker hypothesis sometimes. So you write f of s, the Dirichlet series, which is zeta of s power rho times a Dirichlet series associated to a function, arithmetical function small j. Then you have the relation of small f with small j with a convolution. And tau index rho is associated to the power of a zeta Riemann function. So using Selberg-Delange method, we have an estimate of the sum of tau index rho of n, as we see as we saw before. And then we can use the convolution relation to prove an asymptotic estimate for the sum of f of n. So we have here lambda of j of f. So the lambda j is a linear combination of some gamma h. So is the sum of j of n times log n power h over n. So previous hypothesis imply convergence of gamma of h, so which is a derivative of capital J Dirichlet series in one. Okay. So now, recently, Granville and Koukoulopoulos investigate hypothesis, new hypothesis. So we assume now that the modulus of f is less than the tau index r. R is a fixed parameter. And there is such a hypothesis. So it means that the mean value of f of p is close to rho, in the sense that the sum of gp log p, which is the sum of f of p minus rho times log p, is less than x over log x power a. So a is a parameter, a fixed parameter, but I mean, in the spirit of this result, a should be small, because if a is large, then it's very close to Selberg-Delange hypothesis. Okay, so remember this formula, this hypothesis, and keep in your mind that A should be small. But if A is small, then with this formula, the derivative of capital J may diverge. But if you take the limit of the derivative when s tends to 1, s real and larger than 1, then you can have a nice definition of gamma h. So I add a star to say that it's to quote the small modification of this definition, and it's defined for h between 0 and strictly less than a. Okay, so it's an easy result, but it's very important to be observed. So now we expect one with capital G, J less is a integer part of a minus 1. So the result of Granville and Koukoulopoulos can be settled. So if you have the assumption on the sizes of f and a GP upper bound, then the rest in the asymptotic is less than x over log x power capital A plus 1 minus r, with an additional extra factor. So it's log x power delta of A j plus 1. So delta is a Kronecker symbol. So this means that is 0 unless A equal j plus 1. So lambda j of S are defined as in the classical case, but with gamma H star in the place of gamma H. Okay. So contrary to the pure Selberg-Delange estimates, this does not necessarily provide an asymptotic formula, since rho minus 1, which is the exponent of the main term in the Selberg-Delange result, can be less than r minus 1 minus capital A. So in fact, if you assume that the real part of rho is strictly less than r, and that A is very small, then this relation is possible. So the theorem of Granville and Kokolopoulos only furnishes the upper bound of the sum of f of n. Okay, but if we look at upper bound, there is some very nice result in the literature. So the first result was proved by Hall and Tenenbaum, and after there is some improvement of Tenenbaum, which proves that the upper bound is m of x of f, the sum of f of n for n less than x, is bounded by x over log x power 1 minus r plus capital K times r minus rho. And so the K is a constant. If if f is real, the optimal result is 0.328 and so on. So this means that this upper bound is better than Granville and Kokolopoulos result when for small capital A, so for capital A less than capital K times r minus rho. Okay. And if you restrict yourself to rho equals 0, you can replace capital K by 1 minus 2 over P, little better constant. Okay, so in our work with Gérald, we try to solve 3 questions. So first, what hypothesis can yield a genuine asymptotic expansion, not an upper bound, but an asymptotic expansion? Second, can we relax the assumption side of G of P? So I mean, for example, the assumption such that F need to be less than tau of R. And can we also simplify the proof of Granville and Kokolopoulos? And is there some limitation under GP? I mean, is there some counter example who can show that we cannot prove a better error term? Okay, so let's explain our results. So for the first question, so we recall the convolution. F is two index row convolution with J. And we have the first theorem. So I will explain the assumption. So first, we assume a classical bond for f of p power nu. So it's bounded by capital B power nu. B is a parameter. And we assume also that for any epsilon, f of n should be less than a constant time a power of n power epsilon. So like for an example in a Shu theorem. And we assume that the mean value of f of p, so it means the sum of over p less than x of the modulus of f of p over p is less than or log x plus capital O of 1. I mean, so using this, so this is a weaker condition because we can accept some large value of f of p if they are rare. I mean, in the if it's compatible with this mean value condition. And then we had a very specific hypothesis, an hypothesis on a small interval. I mean, we assume that G of P is bounded in a mean average in the small interval. So I mean that the sum between x and x plus z of G of P times log P is bounded by z over log x power A. So it's a stronger result than GP condition in Granville-Kokolopoulos theorem. But we get a stronger result because we have a bond with x times power log x over log x power 8 plus 1 minus the maximum of 0 and the real value of rho. So you remember that in Kokolopoulos and Granville and Kokolopoulos result, the maximum is replaced by R, which is the defined by the condition that the f of n is less than 2 of R of n. Okay. So it's a genuine asymptotic formula whenever the real part of rho is non-negative. But as we can see, limitation is necessary because if we assume, if we take rho is minus R, so this means so we have a typical example where the real part of rho is negative, then we know that there is some example such that the mean value of f of n is less than x over log x power 8 plus 1. But as rho is negative, I mean the error term dominates the term given by the Selberg-Delange. So I mean it's dominate x over log x power rho minus 1. And this means that in fact we need this kind of error term. We need an error term larger than x over log x power 8 plus 1. Okay, so I give our counter example. So you take f to be the convolution of tau of index minus r with a j function, but j is a multiplicative function defined by p power I over log p power a. So I will show you the proof because it's well, an easy proof, easy to explain. And of course, G satisfies the short interval conditions. Okay. Okay, so the second question is, can we relax the assumption on G and use a simplified proof or a different proof? So for this, we use a friable summation. So I recall that we say that an integer is y friable if all is prime factor is less than y. And I will define what is friable assumption, but it's associated to the y friable integer. And so our theorems 2 is assume that f satisfies GP, of course, but we have this mean value bound, which is not very strong, but stronger than not strong. Well, it's weaker than Granville-Koukoulos assumption, and we also assume a result on the a square value of f of p and also the value of f p nu for nu larger than 2. But it's not really a strong hypothesis. I mean, in a lot of examples is easily satisfied. Then we have the result on the error term, which is we have the same power of log x as in Granville and Koukoulos result. We just reduce the log-log factor in a log-log-log factor. Okay, it's not very important, but it should be quote. Then, of course, the assumption cannot be directly comparable because this assumption is not in Granville-Koukoulos result, but of course, this assumption is weaker than the Koukoulos assumption over the modulus of f. However, our result can be useful if some exceptional value of f of p is large. So I quote an example. So if, for example, if f of the k square prime factor p index k square is k over log x to k. So a very large value, but for very few prime. And please note that the case where a is an integer, playing no special role. So again, the third question, what are the limitations of the GP? We can find f function satisfy GP rho equals 0, such that we have an omega result for the rest. So it's nearly the bond of Koulopoulos and Granville, but with here a minus C times R, and C is less than 1. Okay, so for this example, we choose f of p defined as R time p power ITP, and TP is a step function which has the order of log p power A. So we can define such a function assuming, for example, that TP is constant in a large interval. And if we estimate sorry, the Dirichlet series with the variable condition here, but with in one s equal 1 plus itx, then we have the this approximation. It means that this Dirichlet series is very large, is log x power r. I mean, it's explained that it's why it is a good counter example, because we can show that our there is a best possible bond here, and it's nice to have such a limitation under GP. And if we want to restrict on a real arithmetical function for f, you can assume that f of p is r times the sine of the cosinus of Tp log p. And then we need to restrict to C less than 2 over pi. So this essentially meets the old Tenenbaum estimate. You remember the upper bound that I gave previously. And we have that the summation of f of p over p converge whenever for all a capital A bigger than 0. Okay, so now I have 10 minutes to speak about the proof. So for the first theorem, we have a summation. So we use a summation of j of n over n, but when we fix omega of n. So it's not difficult to say that, to prove that it's close to these summations. So we sum and we restrict log p in a small interval. And we have a product of the sum of j of P over P, and then we can use our short interval condition. And this summation turned out to be the general term of a convergent series in K. So we can bound easily the tail of the series where when K is larger than a constant times log X. Okay, and so we get the convergence of a gamma H constant, well, when H is less than capital J. And we can finish the proof using a convolution argument. And what I want to underline is that we use the Selberg-Delange result. I mean, we use the estimate of capital T index row function, the sum of two index row. So this means our result can be viewed as a consequence of Selberg-Delange method. Okay, so for theorem 2, we use variable summation. So I recall what is variable summation. It was introduced by Duffin, but rediscovered by Fourier and Tenenbaum 30 years ago. And we say that the series sum of AN has variable sum S if we restrict our sum on a y variable integer, there is a limit when y tends to infinity, and the limit is S. There is a very nice example. So if you have never seen such a summation, you can look at the summation over exponential of 2 pi I n theta over n. So we get what we expect plus a term m of theta, which is non-zero for some rational. So for A over Q, when Q is a power of prime. So it's a very nice result. So we say, if the series is summable in a usual sense, and if the variable sum is equal to its usual sum, we say that the series is regular for the variable summation method. So, for example, the sum of the Mobius function over n is classically equivalent to the prime number theorem. It's very easy to handle the variable sum, of course. But the prime number theorem implies also that the sum for 1 over n power 1 plus I tau has a variable sum, zeta of 1 plus I tau, but which is not convergent in a usual term. So it's very useful to use a variable sum. And we prove also with Gérald that the variable summation of Fourier series verified Jordan's theorem, but avoids the Gibbs phenomenon. So what is the Gibbs phenomenon? So I draw some so this is a representation of some partial Fourier series, so which much lot of term, and you see that the upper the supremum of the partial Fourier series is larger than pi. It's larger than the supremum of the function. And you can prove this the result for the bound variation and normalize function. So I take here is one periodic, and we have the convergence, but without Gibbs phenomenon. So it's a nice result. And we have also an upper bound for the convergence if we assume that capital F is a Lipschitz with exponent alpha. So there is many applications. For example, we can prove condition over the convergence. So for which theta such a series is convergent. So when B is t minus the integral part of t minus 1/2. So I have no time to explain the result, but it's a nice result. And if we go back to the Selberg-Delange result, so under GP, we know that the series of G of n log n power h over n may diverge, but the variable sums converge for h less than j. So we use in our proof of theorem 2 convolution relation. So assume that f of y is a g y with a convolution with tour of rho, and we consider f of y. We take y is x power 1/log x, and we use this formula to estimate the sum of f of y of n. And since we have a very accurate estimate of t of rho, because we, thanks to Selberg-Delange method, and using the variable sum of gy, then we get this result for any h, and as the lambda of h of yg can be approximate by the limit when y tends to infinity for h less than capital J, and we have also an upper bound for larger h, then it's just remain to prove our theorem, we just need to handle sum of h y of n, and well, we can prove such a result so the summation is on a shift integer, and after using inductive trick, we can reduce this log-log factor by a log-log-log factor. Okay, so I have no time to give more details. I would like to explain the proof of our counterexample, but I think I will stop here. So thank you for your attention and happy birthday, Balu.
Thank you very much, Régis. Yeah, are there any questions or remarks? Please do not hesitate.
Okay, so yeah, please.
Yes, Emmanuel.
Okay, so I'll go first then. Andrew, for instance, has done a lot on the analogies between integers and permutations, and parts of it extends to this context. So I was wondering if some of your improvements could also lead to new results in that direction.
I don't know, but maybe you see, it's usually if you take some example, very often it satisfies the Selberg-Delange condition or satisfies the GP condition for any A. So it's very easy to apply it. Our work is maybe focused on the restriction. So when you take A very small, what can you expect? So we prove two counterexample with limitation. So we prove also that for if the real part of rho is positive, then we get a better error term. But you know, in general, when we take for application, there is you need to find, well, if on plain example, the GP is easily satisfied, and then it's easy to get an asymptotic, Selberg-Delange asymptotic.
Okay, thanks.
Thank you. Are there other questions or remarks?
Hello.
Yes.
Yeah, thank you. Thank you, Professor, for the nice talk. I wanted to ask you about, is there any relation between the freeability condition and the Riemann hypothesis? So can we say they're equivalent or something?
Well, you know, for in this context, Riemann hypothesis is not very useful because I mean we have a very weak condition of the sum of GP log P. So this means that is the opposite of Riemann hypothesis. I mean, you have a very weak result of the summation of a P. So to assume a Riemann hypothesis here is useless.
Okay. Okay, I see. Thank you, sir.
Thank you. Other questions, remarks? Okay, well, if not, then I think we should immediately start with Jean-Marc Deshouillet's talk, unless people would like 1 or 2 minutes break.
Sorry, I had a small question. May I ask?
Yes, of course.
Sir, thank you for the beautiful talk. Sir, I was just wondering, could you please elaborate a bit more on the inductive trick that enables us to replace the powers of double log by triple log in the last result that you mentioned?
So you mean the counterexample?
Not the
Yeah.
trick. He wants the trick
Ah.
reduces
Yes,
the log logs to triple logs.
Okay. So for the trick, well, you need, so you have a function, and you write it as a convolution of a lot of function, but with R is much smaller. So if, for example, if you take K function, you can divide R by K. So this means that you can reduce the power of log X by K. And this is our trick, well, the idea of our trick to reduce the exponent of log factor.
I see. Thank you, sir. Thank you.
Thank you. Well, thank you for this talk. So Jean-Marc, can you share your screen? And
yeah,
so it's a pleasure to introduce Jean-Marc Desouliers, who will speak on sums of three cubes. Jean-Marc, this is you. This is to you.
One second, please. I try to get full screen. I think it would be better to go to full screen. No? How is it? You have? Is it fine with you or?
It is not full screen here.
No. This is what I understand. So I have to understand how I can go to full screen.
We cannot hear you very well.
Aha. Okay, this is also a problem.
Yes.
Is it better now?
Yes, slightly better.
Only slightly better.
Yes.
I doubt on this I can do really much more. How can I go full screen? Maybe here. I'll try something.
Jean-Marc, what is the problem? Yeah.
Yeah, I try to get full screen, but
even if it is like this, it is okay, but your voice is not audible at all. You're not audible at all.
okay, I try to do something.
Yeah, it's better.
If you click on the rightmost icon on the toolbar, then it should be full screen.
Yeah, but I have no toolbar.
No, you have the upper one. No, not there. Just below that. Yes. So that close to that arrow, both side arrow icon. Just above where you.
That.
Yes.
Okay.
That's.
So this is now full screen.
Yes.
And you hear me better if I shout?
Yes.
Okay. So let us go. So it's really a pleasure. Thanks to the organizer. I was ready to say it is a pleasure to be in Chennai again, but okay, this will be for a next time. So in any case, thank you very much. And so I'm going to speak. When I say cubes, I mean cubes of non-negative integers. Okay, so it started early August this year. Alto Alkan, with a computer scientist in Istanbul, attracted the attention of François Engar, Bernard Landreau, and myself on a sequence in Sloan's project, A267414, and it is a sequence which at that time stopped at 21 and now goes up to 59 with a few holes in it, one hole in 56. And this sequence is the set of integers n for which we know that n factorial is the sum of 3 cubes. And each time it provides such a decomposition. Sorry. So we were really surprised because, as we know, it is not too difficult to see that all the integers cannot be sum of 3 cubes. By the way, we don't even know whether there is a positive density of integers which are sum of 3 cubes. But it's easy to see that you have at most 1/6 of the integer which are sum of 3 cubes, because you look at all the representation up to x, and this is done with cubes which are not larger than x, and with 3 of them the total number of possibility is x, but you have several that will come together, because if the 3 summands are different, which is the major case, then a triple will give you redundancy. An integer, which is their sum, will be also the sum of the one when you turn them. So this was our first surprise with that, because we know even a bit better than 1/6. We know that the cardinality of n, which are a sum of 3 cubes, cannot be larger than 0.1186. Okay, so there was also a second remark that we have no useful algorithm for testing whether an integer larger than 10 to the 30 or so is the sum of 3 cubes. But we have, for example, 55 factorial, which is larger than 10 to the 73. So what is the trick? The trick is the following, that if you take this number, a number with 27 decimal digits, this number, you can run an algorithm showing that it is a sum of 3 cubes. There is no very quick algorithm for testing whether an integer is the sum of 3 cubes. Basically, it is the trivial algorithm. You take a pair of cubes and you look at the sum and you see whether n minus this is a cube itself. There is a slight improvement that has been done by Booker. Maybe I said something about the work of Booker. Recently has been done by Booker last year, which is to remark that if a sum of 2 cubes, x cubed plus y cubed, is divisible by x plus y, and so you can use this to slightly accelerate the algorithm. However, this is more or less the maximum of what we can do. You see this 10 to the 30. So, okay, what does it has to do with the 55 factorial? It has to do the following, that 55 factorial is a cube times this number. And so if you have a cube that is multiplied by a sum of 3 cubes, then it is a sum of 3 cubes. And of course, with the s factorial, you have always a large cubic part. You may say, oh, but is this the cube-free part of 55? No, it's not the case. If it can be divisible, this number n, let us say, can be divisible by 12 to the cube, and then you have something which is really the cube-free part of 55 factorial. It has only 24 decimal digit, but it is not a sum of 3 cubes. So having some cubes help for that. And I chose 55 because it is the worst case. Okay, if you take 59, for example, then with 59, you have exactly the same thing, but this number is with 25 decimal digits. So it turns out that in some cases, you have a cube-free part. Again, this is divisible by 12 to the cube, that the cube-free part may be large or not. And you see, when we are around 59, we are more or less at the limit of what we can do. We expect that we can go up to 60, but not clear that whether we can go to 61 or something like that. So we are more or less besides the value 56, everything has been done more or less what we can do up to now. So, okay. Now, what we want to do, we are not going to prove anything. It is not that, it's not because we don't know anything about the density of sum of three cubes that it's not possible to prove that S factorial is a sum of three cubes, because it has a very large cubic part, so it may be possible. In any case, we don't prove anything like that, but what we do is to get a probability model, you see, like Kramer for primes or something like that. So we try to build a decent probability model for cubes. By decent, I mean that it is consistent with experimental facts concerning the distribution of sum of three cubes. We'll explain what it is. In some way, it is exactly like in the talk of Andrew Granville yesterday. Kramer is maybe not really what we would call the decent probability model for primes, but you would rather try to avoid that an even number is a prime or things like that. So it will be exactly the same kind of thing we are doing. So, and then we have the following. Well, you will see where it comes from, but this is just an artifact of the method, and you can really suppress this. And essentially what it says is that almost surely, as soon as n is large enough and divisible by the first primes to the power 3, then it is a sum of three pseudo cubes. So what is important in S factorial, of course, S factorial will come into that. So in our probabilistic model, almost surely S factorial is sum of three cubes from some point onward. So you see, this value is enough for our model to work, but it permits to consider S factorial because S factorial is divisible by this number. Okay, so let us go now to the some consequences. I will talk about consequences later on. One is for worrying problem with signs. And so it is, okay, I'll talk later about that. And also three non-negative rational cubes. I'll talk about that at the end. So, okay, some heuristic. Heuristic, if you denote by R3 of n, the number of ways to write n at the sum a cube plus b cube plus c cube with a, b, c all pairwise different. And also you may allow two of them to be inside them. There is no big difference, you see, because as soon as you ask that two of them are equal, it means that you write n as something like 2a cube plus c cube, and the total number of representation is something which is n to the 2/3, so it is almost nothing. So we have that the number of representation, this works for R3 and also for R prime 3, this is the same thing, is a certain coefficient gamma with, this is just because you cannot have all the cubes which are large at the same time, and it doesn't permit you to represent a large number. So you have something which will be a bit less than 1/6, which is 0.1186. We'll see the importance of this number later on. So what we may expect is that since the number of representation is 1 on average, or is very small on average, then you expect that you have a Poisson distribution. That is to say that for any k which is non-negative, then the cardinality of n, the set of n, such that R3 of n is equal to k, has a density which is gamma k over k factorial e to the minus k. And so what you expect is that for those which are non-zero, which are sum of three cubes, what you expect is something which is 1 minus e to the minus gamma, because e to the minus gamma just for k is equal to 0. And for the one for which it is non-zero, it is 1 minus e to the minus gamma, and it is something like about 1/9. Okay, so I would like to explain a bit. It has been mentioned already, but what is a random sequence? This is what I want to talk about. So we take a probability space and we take a sequence of independent random variables with values in 0, 1. So Rademacher, I think you call that, the probabilists would call that also Bernoulli random variables. And you consider then psi n to be the indicator function of a set. That is to say that to any little omega in your set, you have a family of values of psi n, and you consider the set A of little omega, which is the set of n for which psi n of omega is equal to 1. And so this is the random sequence. So we are not going to keep all the time the reference to little omega. We say A, which has for indicator function this psi is the random sequence associated to psi. Okay, so in 1960, Erdős, I hope Arkosh is happy with this, and Rényi introduced a random sequence which models the cubes by choosing, you say that the integer n is selected with a probability, which is, what is the probability to have an integer which is around x and which is a cube? It is something like 1/3 x to the 2/3. Okay, and indeed what you have is that for almost all omega, almost surely, the number of elements in your random sequence up to x is x to 1/3. So this is, as regards the number of elements, it is a good model for cubes. Exactly like Kramer will tell you that the number of primes up to x is x over log x in his model. So we consider also the random variable R3 of n, which model little r3 of n is defined by this. It's again not a big deal if you prefer to have then allow that there is something which is equal and show that this counts for almost nothing. Of course, it is this because you see, when you are saying that n is a sum of 3 elements A, B, C in your sequence, let us call them pseudo cubes, is a sum of 3 pseudo cubes, then it means that psi A of omega has to be equal to 1, psi B of omega has to be equal to 1, and psi C of omega has to be equal to 1. And so the product is 1, otherwise one of them is not a pseudo cube, then one value will be 0. So this is nice for expressing this random. And so what they did, they claimed that the sequence R cube of n almost surely follows a Poisson law, exactly what we were expecting in some way, and it is almost surely true in the random model. Well, indeed, there is a gap which was noticed by Halberstam and Roth in their proof, and Halberstam and Roth filled it in the case of squares. In the general case, the proof has been completed by Gogol using moment method, and later by Bernard Landreau, giving slightly different result using correlation inequality. We'll use also this correlation principle. Now there is some real problem with the weakness in this model is that the only case where we can check it with the reality is for squares. And sum of two pseudo squares, you can have exactly the same thing here for squares, and it will give you a slightly different gamma, but it will be also a positive density for sum of two pseudo squares. But we know that from Landau and maybe even before, Landau proved in 1909 that sums of two squares have a 0 asymptotic density. So this is not what I would call as a decent model in some way. We have to modify it. So, for example, also if you look at Barucan, the computation of Barucan in 68, of course, he was not going too far. He stopped at something like about 360, and he found a density up to this point, which is 0.1105. And remember, this is interesting, that it is already below. This is a decreasing function, he observes, and this is already below the value which will be given by the model here, which will give this 0.111 and so on. So we are below this. So again, even for cube, this model shouldn't be very good. This is why it was not clear to understand whether three cubes should have a positive density or not. Well, now we make some computation in 2006, rather long, and check that what we have is that nu3 of x over x, the density, if you go up to 5, 10 to the 14, we did it for all the integer, is something which is a bit less than 1/10. So it is also, this is decreasing, but there's no contradiction here. And by some modular extrapolation, it is something which is slightly a bit larger for x is 10 to the 18, and it seems to converge with something where you have maybe a 4 here or something like that. Okay. Okay. So the question is the probability model we developed with François Encart and Bernard Landreau in 1998. So in the Herder-Shreni model, the set of pseudo-cubes which are congruent to 2 mod 7 has a relative density 1/7. Relative density with respect to the cube. What I mean is that if you count them up to x, you have x cube, cubic root of x divided by 7. But in the real life, no cube is congruent to 2 mod 7. So the question is, how can we take care of the uneven distribution of cubes in arithmetic progression? So what we did is the following. We constructed a random sequence. So what we did the following, well, we cannot take care of all arithmetic progression at once, because if you take care of all arithmetic progression, then an integer which is a cube modulo all the arithmetic progression is simply a cube. So we select an integer k, and with respect to this k, we build a probability model for cubes which agrees with the distribution of cubes in arithmetical progression mod k. So what we do is the following. What we did at that time was slightly different from that, but it is equivalent in some way. And it's maybe easier to present it that way. The probability that Xn with respect to k is rho of Kn divided by 3n. It is not 1/3, sorry, it is 2/3 here. It should be 2/3. Is rho Kn divided by 3 to the 2/3. So in some way we put a compensation. If n is the sum of 3 cubes mod k, then we put something which is the number of representation, yes, well, rho Kn is the number of representation of n as a cube mod k. So if n is not representable as a cube, then n will not occur in our sequence. And if n is a sum of cubes in 3 different ways, for example, then we'll put a weight 3. So it has a nice consequence. First of all, almost surely, the density of the numbers which are sum of 3 elements of AK exist and is independent of little omega. So let us call that delta k. So we have it, and when k, we take a sequence ks, which tends multiplicatively to infinity. Multiplicatively to infinity means that any integer q will divide ks as soon as s is large enough. So you take such a sequence, and then we have a limit, whatever the sequence you choose, with only this property, we have a limit, and this limit is 0.09999425. You see, it agrees really very well with the reality. You remember we were checking something which was 0.09993. And even getting a bit upwards. And also in this model, if you think you can do it for any power, if you look at what it gives for squares, the sum of 2 pseudo squares have a limit density 0. Okay. So now what happens with our first arithmetic probability model? So now we can also show that in our model, the numbers from the arithmetic progression, which are sum of 3 pseudocubes. They have an asymptotic density. Let us call it delta k of QA, and that when k tends multiplicatively towards infinity, then delta k of QA has a limit delta of QA. So first, of course, if you look at the number which are congruent to plus or minus 4 mod 9, then the density is 0. This is a good point, because in the real life, this is exactly what happens. It's not possible to represent an integer congruent to 4 or 5 modulo 9 as a sum of 3 cubes. And of special interest is the fact that if you take numbers which are divisible by the first prime factors, then the delta is of P, the density of the element in this arithmetic progression divisible by this number, which are sum of 3 cubes. This density tends to 1 when a tends to infinity. So really, in this model, it explains in some way why you see a lot of factorial s, which are sum of 3 cubes. Okay, now what in real life, we look at the integer which are divisible by p cube, the product of p cube when p is small. So if a is equal to 1, that is to say you don't ask for anything, and you have the 0. You see 0.99999, so let us say it is 1/10. As soon as you start to put some of them, I don't have the result for a is equal to 2 here. Well, for a is equal to 3, you have something which is almost half of them. If you go up to 5, you have 64. If you go up to 7, and you see that very quickly the modulus, the density tends to 1. So this is also something you have in our model, but you have it also in the real life. Well, you cannot go too far, because you see for a is equal to 13, the modulus is already larger than 10 to the 13. Okay, so now we are going to make, you see, the difficulty with the first model is that you cannot get a result telling you that from some point onward, s factorial will be a sum of 3 cubes. What you say that the density is larger and larger, but we want to do also something for s factorial. So we have to make some connection in some way between the place where we are and ks. So we want to look at the element in this set. We take a model for the cubes which are between s minus 1 factorial and s factorial, and which are divisible by the product of all the elements up to the cube of the primes up to s 1/2 log x. So you have to understand that this is really much larger than ms. A first point I already mentioned is that if you look at s factorial itself, it is a multiple of this number, but this number is rather small. You see, it is something which is exponential in s, even exponential in s to 1/2, where this is exponential of s log x. S factorial is exponential of x log s. So this is really pretty small. Now we take ks, which will depend also on that. So of course it has to be a multiple of ms, because we are interested in saying something for the multiple of ms. And you can choose whatever you wish, which is a multiple of ms and which is less than s minus 3 factorial. So you have really a large choice in that, and the result will be independent of the choice of ks, except that you will ask ks to go multiplicatively to infinity, but it's not even requested. So now we define the random sequence A, we define it by blocks. So in s minus 1 factorial, s factorial, we say that the probability that psi m is equal to 1 is rho of ksm 3m to the 2/3. That is to say, it's exactly what we had in our arithmetical probabilist model. And so this is a okay, so this is what we have, and this is the correct m to the 2/3. And so you have now the complete sequence xi(m) is defined. It's defined for all integer, except that the definition will change a bit whether you are in the interval s-1 s factorial. Okay. So now we have this, we have our random sequence. And so the sequence A is distributed in arithmetical progressions as well as the cubes. You see, if you consider an arithmetic progression kst plus h, such an arithmetic progression, the case rho of ks of h is trivial, of course, there is nobody in this arithmetic progression. So we just assume that this number is different from 0, and it's not too difficult to notice that the number of cubes up to x, the number of cubes, the number of cubes in the sequence between s-1 factorial and s factorial, which are congruent to h modulo ks, is what you expect. And what you expect is just this number. Always you have the local factor divided by s factorial 1/3. And so you have something which will tell you that this is just there exists delta, so that if ks is less than s factorial to the power 1/3, then you have an equivalent for that. And now in the probabilistic model, you have something which is exactly the same thing. So almost surely, now it will be almost surely, if ks is something like small times s factorial n to 1/3, then the probability that you have the number of elements you have in this, I don't know why I have, no, I cannot do something, sorry. So the probability that this number is, looks at this number, the number of pseudo cubes, the number of sum of 3 pseudo cubes, which are, no, pseudo cubes, sorry. The number of pseudo cubes congruent to h mod ks is exactly distributed in the same way. This probability is very, very close to 1. Okay, so now we look at, we turn our attention to the sum of 3 pseudo cubes. So then you will have a singular term which is governed by the local factor, that is to say, the cardinality of triple x, y, z between 0 and k-1, on which are taken modulo k, for which x cubed plus y cubed plus z cubed is congruent to h mod k. And for n in s factorial over 2 s factorial, we have the probability of R3n is equal to 0. This is very small. It is at most, at least we have an upper bound here, which is at most an exponential times some gamma factor and the local factor tau of ksn. Okay, and this is the good order of magnitude. Now we have the following thing, that when you look at R3 of n, so how do we get this, this result? What we do is to say that R3 of n is larger than the number of x, y, z between s-1 factorial and s factorial, which are sum of 3 pseudo cubes. So you see that here we are just, this is because our model is by block. It is easier to consider only the pseudo squares, pseudo cubes, which are between s factorial minus 1 and s factorial, because it is the same law that is behind. Otherwise, the k will be different and you may be in difficulty, but you don't care much, because if you say that already for this number you have something, then you have something here. So the probability that this R3 of n is equal to 0 is at most the probability that this is equal to 0. So you're happy with that. Now you understand also where is the s factorial over 2, that if you take a number which is too close to s minus 1 factorial, then you don't have much margin for writing it as the sum of 3 pseudo cubes, which are larger than s minus 1 factorial. But you see that this is just really an artifact, and we are working on correcting that. Okay. So now what we have is that this is this probability is just at most the probability that we have all this, the intersection of those for which psi y, psi x, psi z is equal to 0. Okay, so this is what you say. You say if this representation is 0, that is to say that nobody has a representation for no n. Okay, so this is fine. So now we owe to Svante Jansson a convenient upper bound for that. You see, the problem with this is that the intersection of this, so this is fine because you can say what is the complementary set of that. Complementary set of that is just the fact that this is equal to 1, that is to say that all of them are equal to 1. This is fine, but probability of an intersection is not the product of the probability because you don't have independence here. And this is really the problem. And this is, by the way, a bit the problem that was faced by Erdős and Rini in their model. So you cannot do that, but Svante Jansson has a very nice upper bound with some term which takes care of the correlation 2 by 2. So this is exactly the product. You are happy, as if they were independent, and you have some correction term, and correction term is you are looking at the intersection in some way 2 by 2 of the element for which you have one of the x, 2 representation where one of the x is common. So you look at all the triple, the pair of triple, which have exactly one element in common. Okay, now you have this, you know that this is fine because this, you know what is, it is 1 minus something, and this 1 minus something, you can exploit it, and this you can also say something about that. So let us go to the next one. So what have we been doing so far? So I am not going to give more here than to say that then we enter into some messy computation, but there is nothing really wonderful. What is fine and what is great is that this term is just an error term. It is 1 plus something, 1 plus little o of 1. It's not always the case with the Jansson inequality. The correlation term may be larger, maybe at least of the same order than this one, but here we are lucky because it is of small order. So we can consider that they are independent. We are happy with that. So I'm not going to go further into this, but just to try to summarize where we are. So where we are is the following. We choose a sequence of moduli, Ks. Ks is a multiple of ms and is less than s minus 3 factorial. This is for the running the computation. Ks has to be small, but even it is much larger than what we have where it makes sense in some way, where we can compare it with the reality. But as in a probabilistic model, it's fine. It's fine. We can define that. So we define a sequence of pseudo cubes, which is defined by blocks. And what we have is, after this tedious computation, what we have is that the probability of Rn is equal to 0 is less than exponential of minus c for some constant, which is more or less the same thing as the gamma factor, times tau ksm. And this will depend on the probability of the residue classes of n mod ks. Okay, fine. So now, and this is for n in s factorial over 2 s factorial, we have this. So I think we have this, and what we want to show is that any integer ns, which is in this set, is a sum of 3 pseudo cubes. So it turns out that we have to work a bit on the singular term. So the singular term is multiplicative. This is nice. It is not a surprise if you are solving a congruence mod, polynomial congruence mod a product of pairwise co-prime integers, then it is the product of the number of solutions. This is fine. So we expect that this will be large in our case. And so we expect some of the factors to be large, the other one being not too small. Okay, no problem. There might be maybe a problem with the prime 3 because tau of 9 and plus or minus 4 is equal to 0. Sure. But if n is divisible by 27, and even if it is 27 times a number which is congruent to 4 or 9, there is no local obstruction again. For example, 27 times 9k plus 4 is congruent to a sum of 3 cubes mod 27 times 9. So this is fine. There is no obstruction. So what we have is the following lower bound for tau p alpha of n. And it is important to have a lower bound because it occurs in the upper bound with exponential of minus the product of the tau. Okay, so it is always larger than 1 minus 2 square root of p. Of course, it is always positive for p is at least 5. And if it is 2 and 3, we don't care because we know that 2 and 3 will occur in our problem with a power 2. So of course, we can also put something here which is positive for 2 and 3, but we are not that much interested in that because alpha will be larger than 3. And when alpha is larger than 3, and n is divisible by p3, then the local factor is at least 5/4. And this is fine because it is larger than 1. So you see that on the cubic factors, we are each time winning something which is larger than 1 and constant, 5/4. And for the other prime factor, we may be losing something, but not too much because this is also close to 1. Of course, it is less than 1, but it is also close to 1. So, okay. So I'm not going to go into this, but you write Ks as the product of the prime which divides Ms, and so they occur at the cube factor, and something which is just positive. You don't care whether they are at the cubic factor or not. You have the phenomenon I was telling you, 5/4 times something important here, which is the number of terms here, and the product of 1 minus 2 square root over square root of qi, but you don't have that many of them. And so tau of ksns is larger than exponential of s to the 1/2 with a positive s. So this is pretty large. So this is pretty large. It means the following, that when we are back to our business, if you look at the probability that ns between s factorial and 2s factorial is not a sum cube, then this bound is exponential to minus something which is exponential of s 1/2. So it is really extremely small. So now if you take all the us, all the element u in s factorial over 2s factorial such that ms divides u, then even the probability that one of these terms is not a sum of 3 cubes is less than, well, stupidly, the number of terms is at most s factorial, so this probability will be s factorial exponential of minus c exponential of c prime s of s 1/2. But this is peanut s factorial compared with what you have won here. This is tremendous. You can see also that we can do something better than s 1/2, but this is not a big problem. And the series over s of s factorial exponentials converges. And so again, our main theorem will follow from Borel-Cantelli lemma. So it tells you that from some point onward, depending on little omega, all the elements which are in US, there exists some S0 depending on little omega, such that any element in the union of all this set, then they are all sum of 3 pseudo-cubes. So it's rather convincing in some way, if you believe in this model. So okay, this is for the main thing. Maybe some other things that now the sum of integral cubes with signs. So there is something which is expected, that sum of 3 cubes, every integer which is not congruent to 4 or 5 mod 9 is a sum of 3 integral cubes with signs. We are rather far from that, because in some cases you need extremely large cubes. For example, for 33, it was solved only last year or 2 years ago, because the smallest summands are of the order 10 to the 16. And it was done by Booker. I mentioned already the name of Booker, and this is where he introduced is the perfection of the algorithm to improve on the greedy algorithm for looking for that. Otherwise, he couldn't have gone that way far. But there are some other small cubes between 100. There is at least one other which is not solved. So the 3 integral cubes with sign, and of course this is so seldom that we don't see how to get some probabilistic model for that. It's completely out of the probabilistic model we have here. But for 4 integral cubes, we expect that every integer is the sum of the cubes and 4 integral cubes with signs. 5 is known, 4 is not known. But here, in our model, we can show that every integer is the sum of a cube with sign and 3 pseudo cubes. Hint, what we do is there is an integer you want to represent. It can be a small one. Every integer is the sum of 4 cubes. So you take an integer a, and you can write a family of cubes ys, such that a plus ys cube is in s factorial over 2s factorial, and so it is divisible by ms. You have to work a bit on that, and then it is a sum of 3 pseudo cubes as soon as ys is large enough. And then you see that you can represent the cubes by a lot of different sequences with polynomial growth and things like that. Okay. So this we'll write down in the proceedings of this conference. I mean, this is called sometimes the easier worrying problem, and if you hear the word of worrying, well, happy birthday to you, Balu. So now there's something else. If you are thinking of rational cubes, then it's a very old result by Riley in 1825. He showed that every positive rational number n is the sum of the cubes of 3 positive rational numbers. There is a proof by Model, who gives a very short proof in 71. He gave a very short proof in 2 pages. And then the question is also to know what can we say when we want to represent n. What can we say of the size of the denominator? And so one can choose the common denominator of the rational to be n squared, big O of n squared. This was proven by Landau and Davenport in 1935, and it was published much later on. And it is in the course of this publication that Mordell was interested in this question. And now the proof is short, but the experiment is worse. Now you see what we think is that ns is in s factorial over 2ms s factorial of ms. If we have an integer like that with large enough s, then ms-ns is the sum of 3 pseudo cubes. And so this is a heuristical support for then of course you can write ns at the sum of 3 pseudo cubes divided by the cube ms. And so this is a heuristical support, if you make some computation for that, for the fact that the denominator should be very small, because you see ms is rather small compared to ns, and so you should have something which say that n is something which is the denominator can be 1 over square root of log n, more or less, something like that. Okay, so I think this is all I had to say. So thank you very much, and again, happy birthday to you, Balu.
Well, thank you very much, Jean-Marc. Are there any questions or remarks after this nice talk? Any question?
Yeah, if I have a question, if I may ask.
Yes, please.
Is anything known about the generating function of R3n, small R3n?
Oh yes, smaller. You see, what you have as always with the additive problems, you have something that the generating function, I mean polynomial generating function, entire series, and this is the root for the circle method, for example. But of course, circle method for 3 cubes will not give you much. But the aim in the circle method is to write the number of representation with a main term and an error term. And if you have something which you expect to be a constant or to be zero, the error term has to be really very small. So in some way, circle method will not give you much, but yes, there is of course, a representation function.
Thank you. Thanks for the nice talk.
Thank you. Other questions or remarks? I have a question. Suppose you take Piateschi-Shapiro powers.
Yeah.
So suppose you take C to be 3.1 or so. What is what is the expected or known density for sums of 4 such pseudo powers?
So the probabilistic model is much easier.
Yes.
Because you see, you have no problem with the arithmetic progressions. So in some way, you can adapt the Erdős-Renyi model, and it will tell you that if C is not an integer, but what you would expect is that each time you take a number of representatives which are 4 times C, such that this number times C is larger than 1, then you have some equivalent, and this the probability model works for that.
And the density will be 1?
Oh yes, for the one which are representable, yes, because you will have the representation function will be, yeah.
Okay, thank you very much. Other questions or remarks?
But what I say that it is in the probabilistic model, of course. It's not in real life. In real life, this was attacked by the way, Zegal in 1933, looked at the number which are now called Piateschi-Shapiro number, but he introduced them even with the same notation, n to the c, and looked at the worrying problem for them, and showed that if you take sufficiently many of them, then you have the thing, and so circle method is working as well.
Okay. Thank you very much. Okay. Are there any other questions? Well, if not, then we can go on with the next session, I think, which will be chaired by Jean-Marc.
Okay.
No, oh, sorry.
Organizer, something to say?
Yes, thank you, Professor Tenenbaum, and let us thank all the speakers of the day today. And we have a small announcement. Anirban will do.
So I just wanted to remind everyone that we are meeting in 35 minutes for the felicitation program, and we'll be very happy if all of you can join. So in 35 minutes. Thank you.